while to get it going, but it's going to be recorded from here on out. Okay, hello, hello. Hope you're all smiling. Okay, what I would like to do is move into getting started with a fundamental theorem of calculus. That is having to do with our actually being able to calculate by hand the antiderivatives that I've been asking you to do to get practice with on the calculator. But we're going to do a couple more of those in just a minute. But I want to start with first the definition of the fundamental theorem of calculus. So what I'd like to do is go to my iPad. No, tell you what I'm going to do. I'm going to go to, I've got the book. Okay, the cable's running across there. I've got a picture there, fundamental theorem, okay? I hope that you can see it. It says part 2. I'm going to talk about part 1 in just a minute. It's a little different, but this is the one that you most has to do with, where you've got to actually physically do calculations and things. And it's making the statement here. Notice how crucial it is, the difference between lowercase and uppercase now. So it's going to matter which one you use. So make sure you do things distinctly. If small lowercase is being used, make sure that's what you use now. And cap f means something different. So let's look at this. Let f be a function. The lowercase f is continuous on a closed interval a to b. If cap f is any antiderivative of f, lowercase f, then the integral of the lowercase dx is a crucial part of it, equals the antiderivative at b minus the antiderivative at a. We're going to do a couple of examples of that in just a second. But this is called a definite integral, where a and b are two values you're given. And every time you're given values in that format, the answer is a number. It's not when we were doing indefinite integrals, the answer sometime was a function and you added a c to it, But this is not that. Notice this also, that cap f of b, normally the antiderivative has a plus c attached to it. And in this case, let's say there is a plus c that we attach to cap f of b. Well, what you're doing is you're subtracting cap f of a, and it's got the same c attached. So you're subtracting it. The c's disappear, they cancel out. So when you've got a definite integral, you do not have to put on a c, okay? But when you've got indefinite integrals, you need to include a plus c at the end of it. But like I'm saying right now, you typically, when you're doing a definite integral, you do not need to include a c at all. It's being washed off, okay? All right, now, let me move on to my iPad, and let's look at a couple of examples of something here. So I'm going to go to my iPad. All right. All right, so here's what we've got. The combination of things. The graph down toward the bottom is the second problem we're going to be doing, but the top stuff in the top half has to do with the same problem, okay? We've got this function, little f of x, and I'm calling it f of x equals 2. It's a simple constant, all right? All right, and remember, all the different problems we've been doing, antidifferentiation is finding the area under the curve. Area under the curve, down to the x-axis. So what we've got is this. We've got this function f, and in a moment, I'm going to be asking you, we're going to do an integral of it, the antiderivative of it, from -2 to 3. Well, let's look at what that value should be, okay? Area under the curve. The graph of y equals 2. That's what we got over here. Y equals 2. What does that look like? It's a line that goes forever to the left and to the right right there. Now, the integral I'm offering there is from -2 to +3. So what the answer to the question should be is the area under that curve between -2 and 3. And you can see that this side is worth 5, and this side is worth 2, so the area should be equal to 10. That is what our answer should be when we take the antiderivative of 2 from -2 to 3. So what I'm going to ask you to do is go ahead and get your calculator out. First of all, do you have a, could you break through and just say, you got a TI 84 or 83? Please say.
84.
Yeah, 84.
83.
84, okay, 84. I haven't heard any 83s. Anybody have an 83?
I have an 83.
Who's that? Jarrett?
It's Jarrett, yeah.
Okay.
So do I.
Okay, Tori, okay, good. Well, that's what I'm working with too. We got to do a little more work than the others do, the TI-84, but it's, I mean, it's not the same, it's the same amount of work, but it's going to be something I'll talk you through because that's what I've got to do too. I've got one in front of me. I've got a TI-84, but it's got an older, it hasn't been updated in a certain sense. So I'll talk about that in just a second. What I'd like you to do right now is everybody, if you would, get your calculator out, and we're going to do that integral of the integral from -2 to 3 of 2 dx. So I'm going to ask you to go ahead and turn on your calculator and hit the math key, third one down, and either arrow down or hit 9. Either way, it should put you in front of this FNINT is what you're in front of with the bracket. All right. Now, those of you that have the 83, when you hit enter on that, you're going to have that at the top of your screen. But those of you that hit enter that have a TI-84, you should have an integral symbol. And I'd like you to go in and click on the bottom box and put in a -2, and then up arrow, and that should take you to the top box, put in a +3, and then go to the right one, and that should put you in the parentheses, just put a 2, and then go to the right one again, and that should take you just past the D. It's stressing the importance of dx in this function. That is the variable that's in terms of that we're taking the antiderivative with respect to, okay? And go ahead and hit enter and see if you get 10. Those of you that have a TI-84, this is what you got to do. FNINT, you type in a 2, that's the function. The function name comes first, and then you put an X, that tells us the variable that it's with respect to, and then you put the A, which is -2, and then the B, which is the 3. Type that in after FNINT and hit enter, and you all should get 10. Everybody getting 10? Anybody not? Go ahead and speak up if you're not. Fantastic. Okay, so, and that corresponds. Go ahead.
We put the commas in.
Say it again.
For an 84, do we put the commas in, or is it just
No,
2x?
you don't need the commas. If you've got the integral sign comes up, then you don't need the commas at all.
Okay.
This is just, the commas are just if you have to make a list, and that's what we have to do with the TI-83. Okay, so let's do this longhand now, okay? I'm going to do it using the fundamental theorem of calculus. And the fundamental theorem of calculus says that if you've got a to b, the function f of x, that's a little f, pardon, f of x dx is equal to cap f of b minus cap f of a. So this is indicating the kind of thing we've got to do. I'm going to ask you to do by hand now the things you've been doing. The calculator you can use to check your work, but the circumstance is this. This is what we're going to do this by hand. We were given f of x, little f is equal to 2. Therefore, we needed to get the antiderivative of it, and you don't need the plus c, I was saying. So all you need to do is take the antiderivative of 2, which means let's stick on an x, right? So that's going to be 2x. So our integral then is going from -2 to 3. So we've got here, I'm going to rewrite this, -2 to 3 of 2 dx. Okay, we know it's 2x. So the notation that's traditionally used, our book does it a little bit differently. I'll share that in a second. I'm going to use what I've been using instead. So what we got to do now is write the antiderivative. First, we write what cap f is, and that is 2x. And now we need to keep a reminder of some kind to remind us what the a and b are. Excuse me, this is -2, and this is 3. Let me wipe those out. So writing a bar of some kind is the way I kind of grew up doing it. In the book, they're showing this kind of thing. They're showing a total bracket and doing -2 to 3. And that just takes a little more work. A simple bar like this and doing that will be totally fine. Okay? And now what you do is, now you do this. You stick b into the function, so it's 2 times 3, minus sticking a into the function, 2 times -2. That gives us 6 plus 4, which gives us 10. Okay? So all you do, the first step is you figure out what the antiderivative is. That goes here without the integration bar. The integration bar says find the antiderivative. We found that, so the integration bar goes away. But we do just have a reminder of what a and b are with that bar afterwards. Okay? Then you do the calculation and you've got it. Okay? Any questions about that so far? All right, tell you what. Go down with me now. Let's do another one. Here's the problem of y equals x minus 2. All right, what I want to do first is let's find the area, use the integration of the area for this portion of it right here. Area from, it looks like it's going from 2 to 6. So what we're going to do is we're going to find the area under that curve. Let's calculate it first. So this is 4, 6 minus 2, and this is 4. So the area of the triangle is equal to 1/2 base times height, which is 1/2 16, which is 8. So the answer, the area of that, so the integral, so that means the integral from 2 to 6 of x minus 2 dx should be equal to 8. Plug that into your calculator now, and then let's do it by hand, okay? Plug that into your calculator and verify that you get 8. I'm going to do it too. So I'm going to do math 9. Math 9. And it's going to be x minus 2 now. X minus 2 is the function, comma, x, comma, 2, comma, 6. So x, comma, 2, comma, 6, close parenthesis, I get 8. Everybody getting 8? Yes, good, 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 good. Okay, you got it? Okay,
What do we type in for D? Or like, what do we put in for
B,
the D?
B is 6. B is 6. It's the right end of that graph, right end of the interval. This right over here, right here is, the interval that we're getting is the shaded region from 2 to 6. So the integral goes from 2 to 6.
I got -8.
Okay? All right, now, let's do one more. This one right here, you guys. Let's do this area down here on your calculator. There's a point I'm going to be making with this. And notice it's under the x-axis. The answer should be negative. Okay? Let's check out what the area is. 2. The area equals 1/2, 2 times 2. So that's equal to 1/2 of 4 is 2. So the area of the triangle is 2. But being that it's underneath the x-axis, it should show up on your calculator as -2. Okay? So check it out. Let's do the integral now. We're talking 0 is the far left to 2 is the far right. Again, it's x minus 2 dx. Verify, I'm saying you should get 2, but the calculator will say -2. So I'm going to do math 9, x minus 2 again, comma, x to get the dx. Then I'm going from 0 to 2. I get -2. Everybody seeing the minus sign? Okay, so one more now. And this one I'm also going to do by hand. So we'll do it again. If you're not getting it totally, Holden or somebody, well, I'll get it in just a second. But now let's do the whole thing. Do the integral from 0 to 6 of x minus 2 dx. And what should you get? You should get 8 and -2 combined. The answer should be 6. Try it. So, math 9. I've got the function again, x minus 2 with my x, comma, okay, 0 to 6 this time. 0, comma, 6. I get 6.
Wait, so
Everybody feeling?
I'm still confused on what you're putting in for x, for where you're putting d of x.
Okay,
Like,
are you using, what do you have, a TI 84 or 83?
I have an 84.
84. Okay, so on the integral then, notice when you do the integral, I want you to put down here for a is 0, b is 6. In the parentheses goes the x minus 2, and then after the d goes the x. That's indicating what the variable is you're working with. Okay?
Okay.
Try it.
Yeah, no, I got it. Because earlier we were putting a number in. We were putting like 5 in for x, so I was just confused on why, like what number to put in for x, but I didn't know we were putting x in, like putting x there.
The x you put after the d.
Yeah, no, I got you. Earlier we were using 5 though, in the first problem we did, so I was just confused on why it wasn't a number, I guess.
Okay, there never was a number that went after the d though. That must have been a misunderstanding because the d was always ex. So
Okay.
on your calculator, the dx is always back there. The 5 was the answer. That was one of the sides of the rectangle, the first
All right.
problem we did. Okay, let's keep moving. Okay, so any other questions about that? If you've got them, please ask. So get the idea, the integration, far left region you're concerned about to the far right, under the x-axis, it's going to be negative area. If you had to do a calculation and answer a question, the area is never negative. But if it's on a calculator and you're doing this type of an arrangement, if part of the graph is under the x-axis, some of it's being subtracted instead of added. Okay? Okay, that's a key point. All right, now, what I want to talk about next is, yeah. I tell you what I want to mention is the idea of what we talked about a little bit earlier in the semester, and that is what's behind me on the board here. Let me go back to me for a second. All right. Why isn't it coming up? Okay, so, all right, got it. All right, now, something that I said, this was part 2 in the book and the definition that was given for fundamental theorem of calculus. Part 1, I'll talk about again a little bit later on, maybe in a class tomorrow or something, but the situation we've been contending with is the fact that when you've got a situation where you've got a rate of change that is your function, the rate of change. So the example that I've got on the board behind me, that vehicle or whatever was going 20 feet per second at the start, and then it gradually sped up. Well, this graph is the change of velocity. That's the function. And it's the rate of change of position. And what is the area underneath it is going to be the sum of the change in the position. So it's going to be the distance traveled. Velocity is distance divided by times. That was a rate. But underneath the curve, it's just distance. How far did you go? There's one problem I give you in sapling, that is water is being poured into a reservoir. by number of liters per hour, okay? Telling you how many, there's a formula for it. Well, if you take the antiderivative of it, then you're gonna get the number of liters. Liters per hour is a rate. You take the antiderivative, you get the number of liters in the reservoir, period. There's another question in there about insects. The population is growing per day. How many insects per day? So if you take you get a functional name for that. You take the antiderivative of it, and it's going to tell you how many insects actually are there that change. What was the change in the number of insects? It was the rate of change before. Well, now it's actually the number of insects. So when you get to the problems, you take the antiderivative over the interval, and the answer will be the number of instead of a rate. Okay? That's the situation. And that's what we had here. It wasn't the number of, the answer was the number of feet that we went. This is a velocity that we're talking about here. And you take the antiderivative, and the area under it is actually the number of feet you went. That's the idea. So we'll be talking about other stuff like that downstream, and that's going to be coming. I'll talk about that more so. So hit the problems in Sapling, and there's 12 of them, and some of them are just really very basic. Use the fundamental theorem, okay? Get practice on it, get good with it. Use your calculator to verify it, but do it by hand. I really encourage you to do them by hand, be able to do the problems by hand, but feel free to do it on your calculator to check your answer, okay? I'll be asking you on assessments coming up to show your work and to be able to come up with the answer, which you can get on your calculator, but I want you to demonstrate you can use the fundamental theorem in that way, okay? Any questions come up about anything that was shared there? Okay, tell you what then. If you don't, I'm going to go ahead then. I'm going to make sure you're all unmuted. And I'm going to go ahead and go through the test now, exam 3. And if you've got questions, when I complete the question, feel free to stop and ask, okay? Let me go through it.
It's not personal. It's just a stand-up, and I appreciate your loyalty. Don't get sensitive, Kathy, but
And all of you, if you did well, don't feel like you have to stay for this. You're welcome to. Hey, you guys, I'm going to go ahead and mute you. It sounds like there's some conversation going on. Okay. So what I've just done is I've muted you. If you want to say something, wait till I finish the problem and then we'll do it, okay? I've muted you because there was a noise going on at someone's mic, and we're going to move through it. Okay, so let's do this. I've got the exam now in front of me, and some of you had some really shining outcomes, people. Your average went up incredibly on this. I see you smiling, Holden. Okay, several of you, Monica. There's a lot of you that did well, and pardon me if I didn't say your name, Tori, okay? But the whole situation is you did well. And let's go through this, though, and make sure you're clear on the logic of it as well, all right? So let's go. I'm gonna go ahead and I'm gonna do it on my iPad. I'll work the problems there. So let's get over there. And if you can wait till I finish the question to ask, that would probably be good. There's several of you on here now. All right. So we're going to hit number 1. All right. So the situation is that you were asked at the beginning to do, it has to do with this function. And you guys make sure now, the rest of the way out, on tests, on exams, on final exam, on quizzes, whatever, make sure you read the instructions, because something I included in the number 1 was include using the first derivative test. There were more than a handful of you that didn't use the first derivative test, and that was a little chunk of the answer, and it's going to be more so downstream to make sure you demonstrate you understand how to use that. First derivative test means we got to take the first derivative and check the slope on either side of the critical number. So let's go ahead and get going on that. So the first derivative is going to be this. 3x squared minus 12x. And I'm going to factor that. Something that happened to a couple of you is that when you got the derivative right, but then when you factored it, it came out incorrect, or you left off a 0 or something. You lost one of the critical numbers in the process of doing it. So setting this now equal to 0, we've got 3x equals 0, which gives you x equals 0, and x minus 4 equals 0, which is x equals 4. All right. Hey, did I start the mic on this? Turn the mic on? Yeah, I did. Okay, good, good, good. All right, so I wanted to make sure I have it because there were a handful of you that aren't here. So let's do this. So what we've got to do is set up a number line. The way I do it is this anyway, and show that to the left, when I get to 0, there's a change that happens, a change in positive or negative slope. So, and most of you that did this problem picked numbers that were close to 0. -1 was common, 1 was common, and 5 were common. Those aren't the only numbers you could use, but that showed up the most. So those are the ones I'll use here. And remember, you're trying to find the slope to the left, in the middle, and the right. So we're going to plug it into f prime of x. So we want f prime of -1, f prime of 1, and f prime of 5 to determine those slopes. F prime of -1 is 3 times -1 times -1 minus 4 equals -3 times -5, which is equal to 15, which is positive. So this is positive over here. Then plugging in 1, I get 3 times 1 minus 4, which is 3 times -3, which is -9, minus here. And then we plug in 5, and we get 3 times 5 times 5 minus 4, which is 15 times 1, which is 15, which is positive, which is here. So it verifies that we're meeting, we have a change of positive to negative here. So there is a local max here, and there's a local min here where there's a negative changes to positive. So all we need to do now is verify what the coordinates are. So when I want to find the coordinates, I got to plug it back into the original function. So f of 0 equals 0 minus 0 equals 0. And f of 4 equals, plugging it back to the original function, is 4 cubed minus 6 times 4 squared equals 64 minus 96 equals -32. So we've got 4 -32. And the idea is we know that it's a min. So local, what did I say first on the quiz? Local min, it equals -32 at x equals 4, and local max equals 0 at x equals 0. Or you could have said the local min was 4 -32, and the local max was 0, 0. Those are both good answers too. Any questions at all on that? Okay, if not, then 1b now, it lends from the fact that if you broke it up and used the first derivative test, then you confirmed, the graph generally looks like this. But if you just went with the graph, I didn't give you full credit on the test. So if I wanted to see some kind of a verification of that, you knew that it was concave up and concave, what was number 3? This is 1C. Yeah, concave up and no, this is 1B was increasing or decreasing. So I wanted to see the work that lets you see that. And if you did the first derivative test, then you've got that it was positive left of 0. So it's increasing over here, and here. So this is at 0, and this is at 4. So increasing on the interval -infinity. Whoa. I need an open bracket there. Where did that come from? Infinity never gets a closed bracket, never. -infinity to 0, and union with, and notice the union sign doesn't have a stem on it. You know, it's not U with a stem. And union with, it's going 4 to infinity. That's increasing also. And we also confirmed that that it was decreasing between 0 and 4. So decreasing, this is 1b, decreasing between 0 and 4. Again, open brackets, because at 0 and 4, it's neither increasing nor decreasing. Okay, questions on either of those at all? All right, let's go to 1C. All right, 1C. This is saying that now you're being asked for concavity. We got x to the third minus 6x squared is the function. Therefore, we need the second derivative test because that's what's related with concavity. But to get the second derivative anyway. There's other ways to do it, but takes a lot more words to have to explain to somebody how you know it's concave down versus concave up. But if you can plug it in, pick a number and plug it into the second derivative, I get 6x minus 12. All right, and while we're here, let's go ahead and set that equal to 0. And that's 6x equals 12, x equals 2. That's going to be the x coordinate for our point of inflection. And there were a lot more of you than was good said that the point of inflection was 2, 0. You picked 0 automatically because when you plug it into the second derivative, you get 0. But you're looking for the coordinate, you got to plug it back into the original function, okay? We'll do that in a minute. Let's first answer the question. We got the second derivative here. I want to take the second derivative at the first critical value, critical number. That's a 0. We get 0 minus 12, which is equal to negative 12. That's negative. So that confirms that 0 we're concave down. And when we plug in the 4 into the second derivative, we get 24 minus 12, which is 12, which is positive here, and that means it's concave up. And the point where it changes is the point of inflection, and that is at x equals 2. So this is at x equals 2. So the circumstance is that we've got when concave up is what I put first, concave up interval. And look, I did a bracket again. These are all open intervals, all open throughout. Concave up we're starting from the point of inflection off to the right, and concave down is point of inflection on the right and negative infinity on the left. Questions on that at all? And then the actual point of inflection was a matter of, we found it. It's where the concave down turns into concave up. You know what? I've muted you guys, and if anybody tried to say something, I don't think you could say anything. Let me make sure I've got you so you can talk. Okay, you are unmuted now. Let me get back on the iPad. Okay, so the situation is that, again, several of you took the 2 where the point of inflection was and you plugged it into the second derivative and got 0 back. The point of inflection, that's always going to be the case. It's going to be 0 when you plug it into the second derivative. So what you need to do is plug it back into the original function, which means you've got 2 cubed minus 6, 2 squared equals 8 minus 24, which is negative 16. So the point of inflection is 2, negative 16. And listen, usually if you're asked to validate that it truly is a point of inflection, typically what you show and the way that it's defined is it's where the concavity changes. So if you go to the left of 2, you'd be concave down. You go to the right of 2, it's concave up. That means it's a point of inflection, okay? So if you ever have to explain that, you need to make sure you show that and say that. Okay, so that's 1D. Any other questions about that? Okay, let's keep moving. The clock is ticking. I want to get through the whole thing here. Let's go to question number 2. All right, number 2 says find absolute maximum and minimum for f of x equals. Notice the last question we had was also a cubic, but it was not on any interval. It was forever. It's just the function. And there wasn't a max or min. On that other function we just did, it went up forever and it went down forever. So there was no absolute max and min. But this one, we've got a little different situation. We've got a cubic, but this time we've got it on a closed interval on -2, 2. And again, on the test, I wrote it as -2 less than or equal to x less than or equal to 2. These two say that these two mean the same thing. Okay, so we got to find the absolute max and min means we need to check the endpoints always. You plug in the endpoints into the original function and you find any critical values and plug those into the original function. So we've got to find the critical values. F prime of x equals 3x squared minus 6x. Set that equal to 0. Some of you, this is where a couple of you, again, you lost one of your factors because you lost the 0. You got 0 equals 3x times x minus 2. There were a couple people that got x minus 6 there. There's just a math. And when you got that wrong, it threw everything else off a little bit. But this 3x, that x out there means x can be 0. X is a critical number. And x minus 2 determines the other. So 0 and 2 are the critical numbers. So the thing you need to do with this then is check both endpoints, and one of the endpoints is one of our critical numbers, so there's nothing lost there. And the other critical number is in between -2 and 2. So we need to check all 3 of those points. So f of -2, f of 0, and f of 2 are 3 points. We need to get the value of those and find out the biggest one is going to be the absolute max. The smallest one is going to be the absolute min, okay? So we plug it in back to the original function. Notice this, we're trying to find the maximum value of the entire function. So -2 cubed minus 3 -2 squared plus 20 equals -8 minus 3 times 4 is minus 12 plus 20. We got minus 20 plus 20 equals 0. So we've got -2. 0 is our first value that we're checking out. Now f of 0 equals 0 minus 0 plus 20 equals 20. So we've got 0, 20. That is our second value. It's the biggest one so far. Let's see what we get here. 2 cubed minus 3, 2 squared plus 20 equals 8 minus 12 plus 20. -4 plus 20 equals 16. So we've got 2, 16. The maximum value is here. The minimum value is here. So absolute max is equals, I'll say even equals, the biggest value it ever gets is 20 at x equals 0. Absolute min equals, the smallest is 0, and that happened at x equals -2. You could have also said the absolute max was 0, 20, but it's actually asking you what is the absolute highest value this function ever gets, and that's equal to 20. And you could have said absolute min was -2, 0. Could have. But absolute min, saying what the value is making it clear that you get the concept. Questions on that at all? Okay, let's hit number 3. Clock is ticking. Got to keep moving. Pardon me if I get long-winded on things that you already know. I want to make sure everybody's together on this. Number 3 now, this is find the limits, and it's got L'Hopital considerations. One of them, you don't need L'Hopitals at all. This first one, limit as x goes to 0 of 5x minus sine x over x. So first thing is you plug it in, you plug in 0 and see what the outcome is. Several of you left it off. You didn't do this step, and I took off, I varied how much I changed, I lessened the amount I took off for it, but I still took off 1.5 points out of 5. So this is an important part of the problem, is does it qualify to use L'Hopital? Plug in 0, I get 5 times 0 is 0 minus sine of 0 is 0 over 0, which is 0 over 0. Yes, it qualifies. That means I can use L'Hopital's rule, which says the limit of this function is equal to the limit of the same limit with the derivative of the top over the derivative of the bottom. A couple of you use notation that was the derivative of the whole thing. And the derivative of the whole thing would require the quotient rule. That's not correct. So you needed to say the derivative of the top is 5 minus the derivative of sine is cos over the derivative of x is 1. So now we plug in 0 and we get 5 minus cos 0 over 1, which is 5 minus 1, which is 4. There were a few of you that automatically jumped in and you made the cos 0 equal to 0. It was just an automatic reflex action. I don't think you thought about it. I don't think you didn't plug it into your calculator. The cos at 0 degrees is 1. That's the x value over there. So the answer is 4. Let's do that. A. Let's do B. Questions on A. Make sure you speak up, okay? Sorry if I'm talking a bunch. All right, so now we've got sine x over e to the x. Several of you jumped in and took the derivative of the top and the bottom. That misses the point, okay? You plug in 0 and you find out L'Hopital doesn't apply here. You plug in 0 and you get the sine of 0 over e to the 0. And if there were a handful of you that got e to the 0 equals 0, problems. E to the 0 equals 1. A sine of 0 is 0 over 1 is 0. You're done. That's it. It's not indeterminate form. Therefore, you do not use L'Hopital's rule. That is it. The answer is 0. Okay. Questions on that? Okay. Limit as x goes to infinity of x squared over e to the x. Okay, again, we're running this one to infinity. So as x squared goes to infinity, as x goes to infinity, x squared goes to infinity. As x goes to infinity, e to the x goes to infinity. So we get an indeterminate form of infinity over infinity, so you can lose L'Hopital's, which says that this first limit is equal to this same limit with the derivative of the top over the derivative of the bottom. Check it out. What do you get? Again, 2x goes to infinity. E to the x goes to infinity. Therefore, we can do it again. And now, this time, there were a couple of you that did it one more time after this. And when you get here, it's no longer infinity over infinity or 0 over 0. It's 2 over infinity as it goes along. So you got 2 over. This thing is going to infinity, and as that goes to infinity, this thing's going to 0. So the answer is 0, but you've got to check L'Hopital's a couple different times. Use L'Hopital's a couple different times. Okay, let's do D. D was the limit as x goes to pi of 1 plus cos x over sine 2x. All right, so here's the situation. You plug it in, let's see what we get. As x goes to infinity and x goes to pi, we get 1 plus cos pi over sine of 2 pi. Okay, now get on the unit circle. pi is here, 180 degrees is pi, and then 2 pi is back over here, okay? Cos is the x value. X over here at pi is -1. So we get 1 minus 1. And at 2 pi, the sign is the y, that's 0. So we get 0 over 0. That means it qualifies for L'Hopital, which means we write the same limit, but take the derivative of the numerator and the derivative of the denominator. The most common answer, there were 2 common answers that happened, 2 mistakes that were made on this. The first one was derivative of the top. Several of you came up with 1 minus sign. The derivative of 1 is 0. So it ends up being just minus sign. And on the bottom, you didn't use the chain rule. There's a 2 in front of that x, so you got to use the chain rule. So the derivative of a sign is cos of 2x times the derivative of 2x is 2. Put a 2 in front. So now plug in pi, and we got minus sine pi over 2 cos 2 pi. Okay, at pi, the y value, the sine of y, that's 0 again. We got 0 up top. And cos at 2 pi, we're at x out here is 1. So we got 2 times 1, which is 0 over 2, which is 0. Okay? All right, now let's go through kind of quickly the last one, which you guys handled the best. I think this one was more uniformly correct answer on the test. This question was the best score out of all of them. And that was to find the, there were a couple of mistakes that happened. One of them is a couple of you did 2x plus 2y, which means you were trying to find the area of, it was only with 4 sides of a rectangle. But it turned out to be number 4 turns out to be 1,600 feet. Excuse me, 1,600 feet of F fencing, and we know that the fencing is the diagram is like this. If I use x on the sides and a wall here, then this is my y. So I got 2x plus y. Therefore, the formula combining these two is 1,600 equals 2x plus y. That's the constraint formula where we're going to be able to do our substitution from. But then we've got the one we've got to take the derivative of is we're trying to maximize the area. So we need to take the derivative of this function, solve for y over in this one, and substitute it in y into the other. So a equals x times 1,600 minus 2x, which equals 1,600x minus 2x squared. And there is our a in terms of x. Now we take the derivative of that because that's what we're maximizing. A couple of you solved for x, and that made it a little more complicated. I can do that in a minute if you want. If you did that and like to stay after and get with me, you can. I'll talk about it. But now we take the derivative, and we end up with 1,600 minus 4x. Set it equal to 0. 4x equals 1,600, x equals 400. Therefore, y equals 1,600 minus 2 400s. So that's 1,600 minus 800, which is 800. So y is 800, x is 400, area equals 400 times 800, which is 32 and 4 zeros. And that is feet squared since it's area. Max area, so max area equals 320,000 feet squared. Questions on that? Okay, it's 1:50, so officially I'm going to stop. But does anybody have any questions about anything you want to talk about? You did a problem differently or something like that?
I thought
Okay,
that the number 4
Yeah.
included I thought you were supposed to include the wall. So I did 2x plus 2y.
Yes. But what made you remember in the problem, it had said that the way it was worded, so you don't include the wall.
I
The
thought in
wall-
this one it said to include the wall. Because I remember on a quiz we had a similar question.
It says the wall will be one of the sides.
Yeah, that's
I'm
why I
sorry if
thought,
that was misleading. There were three, the other three would be fencing. So you took it that the wall was fencing also then, huh?
yeah, I took it as you have to include the wall.
The wall was one of the sides of the rectangle. So that, I think that that's kind of saying the other three aren't that means one of the sides isn't going to use any fencing. So the wall, a long straight wall, the wall will be one of the sides and the other three need fencing. Okay, I tell you what, I'll relook at that. I thank you for saying that. That's how you saw it. That's how you read it. Very good. I'll relook at that. That's good.
Okay.
Thank you for telling me. Okay, so anybody else have anything? Jack, you doing all right?
Yeah, I'm all good.
Good. Blaine, you smiling? Blaine, you smiling?
Who's Blaine?
Okay, good. Jasmine? Sizzling? That's good.
Yeah, all is good.
Good
All is
example.
good.
Good.
Yep.
Gabe, you doing all right?
Yeah, I'm doing all right.
Okay, good. Good exam.
Yeah, Dr. Winter.
Okay, well, listen, be in touch. I'll be back in touch with you about something I'm thinking about for tomorrow, okay? I'll be
All
in
right.
touch shortly. Hey, good, Blaine. That was decent. Yours was decent also. There were a few slight little things that bit again, but you're right on.
Yeah.
You got it. You nail the final.
I'm going for it, but it's Blair, by the way.
No, you're doing fine. Keep doing what you're doing. Make sure get in sapling now, okay?
Yeah, I gotta get on that. Thank you.
Okay, great.
See ya.
Bye-bye.